This is essentially a review paper that was co-authored by myself, Aaron Curville, and Pascal Vincent, and published last year in PAMI Transactions. So it's a long paper, and I only have about 20 minutes, so I'll only talk about some of the aspects in the paper. The paper goes through a discussion about why representation learning is interesting, and some of the successes of deep learning. So I'll be very brief on that. I'll talk more about what is it that we mean by a good representation, which I think is still a somewhat open question, and I introduce the notion of disentangling of the underlying factors of variation. The paper then goes through discussions about various algorithms to learn one layer of representation, for example, with the sparse coding, RBMs, and autoencoders. I guess there's something funny going on here, but the missing thing at the end here is about something I will spend more time on, which is a probabilistic interpretation of regularized autoencoders as a generative model, something that has happened more in the last year. So the point of view that I want to put forward about machine learning here is trying to put together the geometrical interpretation of what is going on with the probabilistic interpretation. Essentially what I'm thinking of is generalization as trying to guess where to put probability mass. So the where is the geometric part. And the challenge is the curse of dimensionality coming of the just the exponential number of configurations we want to look at. And the kinds of problems I'm interested in are those that we look at in AI tasks, such as in perception or dealing with natural language, where probability mass concentrates, so you have this idea of manifolds. And the evidence for this is that most input configurations are very unlikely. If you try random pixel configurations or random sequences of letters, these are very unlikely. And so what we were trying to do is essentially take probability mass from the empirical distribution and find where to put it. And you can use smoothness, which is the usual thing we do in non-parametric methods, but it's not enough. You want to discover some kind of structure that allows you to generalize between the data points and even extrapolate. And one of the main tools that has been used in representation learning, so the kinds of things we talk in this paper, is compositionality. Compositionality is what helps us to deal with this curse of dimensionality. And it comes in two flavors. One is the very old idea of distributed representations or embeddings or feature learning, where you're going to learn a bunch of factors or a bunch of features that are not mutually exclusive and that can give you a combinatorial number of configurations. And then the idea of composing these things at multiple levels, that's the idea of deep learning and deep architectures. So all of these are essentially priors. They don't have to be true for your particular data set. But the bet is that for many of the data sets we care about, especially for AI tasks, this is useful. Let me come back to this idea of distributed representations and why this is an interesting concept, a very old one. Think about clustering problems or many non-parametric statistical problems where the way we deal with the learning issue is we take the input space and we break it into regions, maybe in a soft way, and for each of these regions we can have separate parameters or data points that tell us what to do in these regions. And so the number of different regions that our function can represent, which captures the complexity, the ups and downs, the number of variations, goes linearly with the number of examples or the number of parameters. Instead, there's something you could do that might be better if you assume something more about your data. And that's what we do with these methods, like in RBMs or auto-encoders or neural nets or sparse coding, where you imagine that your parameters are going to be used to split the data into various ways, and it's the combination of all those splits that gives rise to different regions. So imagine a bunch of two-way linear classifiers. Each represents a bit that tells you you're on the left or on the right of these hyperplanes. And now the number of configurations can go exponentially in the number of parameters in the number of these hyperplanes. And you can get statistical efficiency through this, but of course it's assuming something about the data. It's assuming that these different factors make sense, meaningful, and so you can talk about regions for which you've never seen data, something you couldn't do in the left-hand side with the traditional methods like clustering and nearest neighbor and Gaussian kernel machines. the next twist is to think about how these factors arise, that, these attributes that you're going to be learning, instead of thinking of a simple linear function in the input space. These may be more complicated functions, and the way to do that is to compose them to have multiple levels of these representations, and that's what deep learning is about. And there's motivations from theory. There's a string of papers. Most recent, just last week, we presented a paper at iClear, the learning representation, the conference on learning representation, which show that there are some families of functions that can be represented exponentially more efficiently if you allow yourself to use these deeper circuits. There's, of course, motivations from the brain and cognition, and there's motivation I'll mention later, which is having to do with sampling models that are structured in this way, where we found that mixing between modes is much better when you do it at more abstract levels of representation that have been learned. Finally, the real reason why there's been so much excitement about deep learning is because they have been essentially practical breakthroughs. They have achieved state-of-the-art, often by a large margin, on a lot of industrial scale AI tasks, such as object recognition, speech recognition, language modeling, and music modeling. And just to show you a little bit of that, in speech recognition in the 90s, error rates were going down. In the decade that followed, even though computing and data improved, performance didn't improve much, and then people started using deep learning methods. Same kind of thing has happened more recently with object recognition. That's the kinds of error rate reduction that were observed, for example, on ImageNet, 30 to 50% error rates reductions on these two kinds of tasks. All right, so let's get back to something interesting and fundamental, which is how to generalize, and in particular, how do humans generalize from so few examples to a new class, a new task. And basically, I believe it's because they're exploiting all of the learning they've done before, so that's transfer learning. And the hypothesis here is that the way that transfer takes place is because we've built this model of the world, which essentially is representations of what we're observing. And good representations allow us to generalize very quickly. An example of that is shown in two competitions that took place in 2011 on transfer learning, where we use these layer-wise learning of representations, unsupervised learning, RBMs, and denoising auto-encoders and others. And these competitions, there were results presented at, one was at NIPS and the other at ICML. And what the pictures show are the accuracy versus the log of the number of labeled examples. And you'd like these error curves to be as high as possible and to rise as fast as possible. And what you find is that if you learn better representations here in a purely unsupervised way, the learning curves get better and better for at least this particular data set, on which the effect is pretty impressive. So now let's get back to the very basic question of, all right, so if we learn good representations, we can generalize much better, but what does it mean? What is a good representation? So there's a very old notion that's very popular in computer vision in particular, which is the notion of invariance. And we'd like to have representations that correspond to features or factors that are invariant to the things we don't care about. But I'm interested in unsupervised learning. I would like to be able to learn from lots of unlabeled data. And so what does it mean to be invariant? Invariant to what? We don't know what the task is going to be yet. So instead of talking about invariance, I'd like to talk about disentangling. So if you're doing speech recognition, you'd like to be invariant to speaker characteristics. But if you're doing speaker identification, you'd like to be invariant. You want to keep that information. You be invariant to the phonemes that are being presented. So instead of being invariant, what you want is to disentangle the underlying factors. Of course, you don't know what they are. So the question is, can machines discover these underlying factors? And that's what I call disentangling factors of variation. The funny thing is, if you stack RBMs or auto-encoders on top of each other, you find some form of disentangling happening, even though we haven't programmed this in. You see higher level features specializing more to the true underlying factors, to some of the factors, and then being insensitive to other factors. Not completely, but to some extent. So something is happening and we don't fully understand. So what I believe is that in order to really endow machines with the ability to disentangle the underlying factors of variation, we need to put in some prior. It's not going to happen magically because you can see it's an ill-defined problem. What are the real factors there? So there's going to be statistical structure that's going to be emerging from the data, but maybe we can help the learner by putting in some prior. So the first prior is that there are such factors. That's the idea of distributed representations. And the second prior I already talked about is that these factors are organized with multiple levels of abstraction, and that's the depth prior. But there are other priors that we use commonly that have been used in deep learning research. One of them is semi-supervised learning, where you're assuming that the thing you want to predict y is one of the factors that explains the variation in x. It's a prior, it doesn't have to be always true. The multitask learning approaches also exploit a similar prior, which is that different tasks share a subset of the factors. Then one of the group of priors that I want to talk about a little bit more here is used for example, in auto-encoder research, is the manifold hypothesis, that the probability mass is concentrated, and furthermore, that different classes correspond to different manifolds that are usually well separated in most places. Then there's a lot of work exploiting the idea of temporal and spatial coherence, which is saying something about some of these factors varying in time and space. Sparsity can also be seen as a prior. It's saying that, in this context, that for any particular example, most factors are irrelevant. And finally, there's a prior that's being neglected, I think, in thinking about how to build good representations. And I call it the simplicity of factor dependencies. It says that in the right representations, the relationships between the variables or the factors should be simple. Independence might be an extreme case, but in general, just simplicity of the dependency would be a good thing. Now, let me go to autoencoders and what we call regularized autoencoders and the relationship with manifold learning. So think about your data, your empirical distribution in the case where data is coming close to a low-dimensional manifold. So what are we going to do with an autoencoder or a representation learning algorithm in general? We're going to try to take each data point and map it to a representation such that we can recover the original data with some small error. So that's minimizing the reconstruction error. And that means that our representation should preserve information as we move along the manifold, because I want to distinguish that example from its neighbors. On the other hand, if I move orthogonal to the manifold, I don't care about that information, so I can throw that away. And if I have a regularizer, which tells me that my representation should be as simple as possible, so invariant to everything, if it can, then we can throw that information away. And what's going to happen with this is that the representation we're going to be learning with these autoencoders is going to act like a coordinate system for the manifold. And we've done experiments to show that actually happens, but the ideal picture, what we have in mind, is that if you take the derivative of the representation with respect to the input, so that's the dh dx, so this is a Jacobian, at any particular point there's this Jacobian matrix, and it tells you which directions in input space your representation is sensitive to. And if you look at the spectrum of singular values of that matrix, it tells you how sensitive the representation is to different directions in input space. And if that spectrum is a nice square like this with d leading dimensions that have a high sensitivity, then it means you really have discovered a d-dimensional manifold, d-dimensional coordinate system. What we actually find in experiments are things like this, like the red curve. This is, again, now this real data, a Jacobian of coming from a contractive autoencoder. And if we regularize the representation here with this contractive term I want to explain, you get much sharper spectra than if you use regular autoencoders, which is the black curve. And then you can look at these derivatives and the leading singular vectors, and you can see that they really span the space of variations that's meaningful here. Each of the images on the right is one of the leading singular vectors corresponding to a tangent to the manifold that has been discovered, you can do it. You can then combine these with the data in order to generate nearby examples, and you can do it with any input, and you get a different kind of tangent, of course. And if you try to do these things with methods like local PCA, which you think also can capture the manifold structure, because there's no sharing, there's no distributed representation, you don't find such nice things. If you do it with these regularized auto-encoders, you find that the leading the tangent vectors are meaningful. They correspond to adding parts and moving parts. Now, let me tell you a few more words about the denoising autoencoders, one of these regularized autoencoders, because in the last couple of years, we've made progress understanding its probabilistic interpretation and how it captures the input distribution. So what the denoising autoencoder does is very simple. It has an encoder function and a decoder function, which you can parameterize as you want. And the way it's trained is to minimize a log likelihood reconstruction, so it outputs a distribution over the input space given the hidden units. And you want to make that reconstruction distribution give a high probability to the correct input. But what you give it as input is not the raw input. You give it corrupted input with noise added, maybe some inputs set to 0, like in dropout, or Gaussian noise added, or whatever you want. And geometrically, what is going on is that if your data lies near a manifold, what we do with the corruption is we essentially move it out away from the manifold and then ask the learner to learn this mapping from the noisy examples to the clean examples. And in basically the difference vector between the reconstruction and the original noisy input is going to build a vector field. And actually, you can draw this vector field, and you can prove that actually you get an estimator of that vector field. So if you minimize this regularized reconstruction error, you can show that the difference between the reconstruction and the input is a vector that points towards the direction of higher probability and is in the limit with continuous input, Gaussian noise, squared error, and the noise going to 0. You can show that this is a consistent estimator of this gradient field of the score, essentially. There's been a generalization of this to this year at the last NIPS to a more general setting where the input doesn't have to be continuous, it could be discrete. Of course, we don't talk anymore about the score, and the reconstruction can take any, distribution can take any form. I'll come back to that later. Now, in the last few minutes, I want to mention something that has arisen out of our work with Boltzmann machines, RBMs, and the Boltzmann machine, which is really difficulties in training these beasts that come from two issues. One is that it's hard to mix between modes when your model becomes very sharp, and as your model gets better, it's hard to mix. And we need this mixing in order to estimate gradients and to train the model. And the other issue is that the number of modes of the distribution can be very large, and that's going to kind of break the assumptions we're making when we use MCMC to estimate our gradients. So the first problem, mixing between modes, comes because as your density model improves, especially with the manifold hypothesis, it's putting probability mass on sharper and sharper places, and it becomes hard to mix between those modes, exponentially hard. So training seems to be stalling. One thing we found that is interesting is that if instead of sampling in the input space, you run your Markov chain in higher level representations, for example, in a deep belief net, what we do is we stack RBMs, and when we sample from the model, we're really sampling from the top level. Then mixing is much easier in the sense that it mixes between those modes much faster. And we've done a lot of experiments reported at the last ICML. And in trying to understand that, we find that what happens is that those learned representations take these manifolds that are highly curved and thin and blows them up and flattens them up. So if you do a linear interpolation between examples, here it's an image of a 9 and an image of a 3. In pixel space, the linear interpolation looks like an unplausible configuration, of course. You just add up the images. But if you add representations in the higher levels of the system, and then you interpolate there, and you project back to visualize these things, you see that the interpolated representations correspond to meaningful inputs that have a high probability. So what it means is that those manifolds, which were highly curved in input space, become flatter in the higher levels of representation. So that's really good news, and it also probably explains why mixing is much easier there. The second problem of many modes as something that seems harder to deal with, but it turns out that the recent work with the denoising auto-encoders probabilistic interpretation may give us an interesting path towards dealing with this. So in traditional probabilistic models, we directly learn a probability distribution, P of x, that we parameterize, and we have some equation that tells us what P of x looks like. Instead of doing this, which is the dominant way of doing probabilistic modeling, what if we consider that we're going to build a machine that generates data, and the machine, like a Monte Carlo Markov chain with a transition operator, and the machine that generates data has parameters, and we're going to tweak the parameters so that the machine is going to generate data from the right distribution. In other words, that's going to estimate the data generating distribution. It turns out that you can do that. So how would that help us with the problem of many modes? So the problem of many modes especially comes up when you have you want to estimate the gradient through a partition function that involves summing over all those modes, and so the estimation of the gradient of the partition function is something unreliable, and we use MCMC methods, and it's very noisy, and it may be one of the reasons why we are having trouble training really large Boltzmann machines, for example. And in the picture, what we see is a distribution P of x that has many, many modes, and so computing expectations over that is going to be very hard and unreliable. Instead, if we consider a conditional distribution of one step of a Markov chain that goes from xt minus 1 to xt, that conditional distribution may have fewer major modes because it needs to only make a local move in the space of the data. And so because the number of these modes is much smaller, the partition function of that conditional distribution should be something much easier to compute, and its gradient should be much easier to estimate. And that's what we get when we train this machine that generates data as steps of a Markov chain. Really, we're training this conditional distribution, and so we're taking the hard problem of averaging over a huge number of modes into something that looks more like supervised learning. We're trying to do something that learn a conditional distribution where the output distribution is now much simpler than if we are trying to do directly P of x. All right, so I think I'm getting close to the end of my time, but in our last NIPS paper and the upcoming ICML paper on denoising auto-encoders and what I call generative stochastic networks, we have theorems showing that if you train with this reconstruction error principle, you can get a consistent estimator of the underlying data generating distribution through this Markov chain that is implicit, that comes out if you take the trained system and you apply it iteratively. So for example, with your autoencoder, if you just corrupt encode, decode, corrupt, encode, decode, that defines a Markov chain. And what we show is that if you have a consistent estimator of this conditional distribution which tries to recover the clean input given the corrupted input, then the chain converges to a stationary distribution that is also a consistent estimator of the data generating distribution. So as you get better at learning these steps of the Markov chain, then the Markov chain itself has a stationary distribution that estimates your data generating distribution. So it does what we wanted, what I was trying to tell you about earlier. There is some more recent work that I won't have much time to talk about that's interesting, that connects autoencoders with directed graphical models with latent variables. There's people at DeepMind and Maxwelling and colleagues have been producing recent papers on that subject, which I also encourage you to look at carefully if you're interested in this area. And I'm now going to conclude that deep learning has been very successful, especially in industry recently, but I think there are lots of really interesting challenges in unsupervised learning. And it raises questions about what is a good representation and how to disentangle the underlying factors of variation. What I've tried to tell you about here is a little bit about some of the algorithms that have combined both a geometric perspective and the probabilistic perspective in order to model the data. And well, I hope you got some of it in spite of the fact that there's so much material compressed here in a short amount of time. Thank you.
Thank you. My question is about learning representation for texts.
Yes.
How do you think, what is better to do to train a topic model like LDA or to train a deep autoencoder?
Right. So topic model is essentially a clustering method. So it's going to suffer from the kind of statistical inefficiency I was trying to explain in this slide. And a deep autoencoder, I think, is going to be harder to train because the optimization problem is more difficult, but it can potentially generalize a lot better. And there's a lot of recent work learning embeddings with what's called neural language model that have now become really dominant, at least in some areas of natural language processing, especially language modeling.